All right, hello everyone. Welcome to our episode today for OpenHW TV. It's a great episode with our OpenHW Accelerate program. And as we do with all of our content on OpenHW TV, we pre-record a bunch of the session so that it improves, user experience, viewing experience. All of our panelists are with us here today, watching the live stream together with the attendees. And we'll be accepting, so you guys can all give a wave to say hello. We'll be accepting questions throughout the recorded session. So please enter your questions in the Q&A chat box. And we'll come back live at the end of the pre-recorded. It's about 25, 26 minutes in length. And we'll come back live and have a good half hour to take those questions and hopefully have a lively Q&A session. So here comes the live stream, and we'll see you again in about 25 minutes or so. Thanks for attending. Well, hello, everyone. Welcome to OpenHW TV, Season 2, Episode 3. Today's episode is a very exciting program where we're going to provide details on an innovative co-funded research initiative called OpenHW Accelerate. And in today's session, we'll hear from Mel Char from Mitacs to give an overview of the OpenHW Accelerate program. And then the participants in the first project that we've awarded under this program related to RISC-V vector research. We'll hear from Gord Harling from CMC Microsystems. We'll hear from Frank Urkeniak and Matthias Cavalcante from ETH Zürich. And we'll also hear from Yvon Saria and Hossein Askari from Polytechnique Montreal. But before we get into the details of the project, I'll first provide a quick overview of the OpenHW Group. So the OpenHW Group is a nonprofit organization with a global footprint that is focused on providing an infrastructure where hardware and software developers can come together to curate open source IP and related tools, software environments, and peripherals, all for the benefit of creating these open source artifacts in line with industry quality verification work. The first few projects that we have are all related to RISC-V open source cores called the CORE-V family. And these cores are available under a permissive open source licensing model and freely available to anyone who wants to use them. And they've been verified to industry quality verification standards. We have a broad ecosystem of over 63 members within the OpenHW Group ecosystem. On the industrial side, we have very large systems companies and semiconductor companies participating, as well as smaller companies across the whole breadth of the ecosystem from a tool chain standpoint, software standpoint, board level, chip level, and IP level as well. We also have a very rich research ecosystem, and we'll be talking with a couple of those institutions in this episode today, and also a partner ecosystem to help us curate these cores and bring the technology to the ecosystem. The way that we're organized within the OpenHW Group is through a series of working groups and task groups. We have a technical working group and a marketing working group, both of whom report into our board of directors. And underneath those working groups, a series of task groups to execute the various projects that we have underway. And in today's episode, we're going to be hearing primarily from the University Outreach Task Group within our marketing working group that is responsible for the OpenHW Accelerate program. So what is OpenHW Accelerate? This is an exciting multi-year co-funded research initiative with upwards of $22.5 million of research funding available. $4.5 million on a yearly basis, and 75% of that funding is to be spent on Canadian universities, with 25% spent on international institutions. And in today's first project, we'll be hearing from ETH Zürich and Poly Montreal as they go through the research project that we have today. The OpenHW Accelerate initiative is managed by our University Outreach Task Group within the OpenHW ecosystem. That task group is chaired by Mel Char from Mitacs, who you'll hear from today, and Hugh Pollitt-Smith from CMC Microsystems. The research tracks that we're interested in for OpenHW Accelerate are really trying to focus on some of the key market drivers in today's technology space around a reduced power envelope, purpose-built accelerators for AI and ML, and heterogeneous clusters. And in particular, we want to curate projects across 5 application tracks: IoT, mobile and wireless, automotive, memory and storage, and cloud and data center applications. And you'll hear today's edge-based application focus with the Vector Accelerator project. So with that, I'm going to bring in each of these speakers to give some opening statements before we open it up to the live Q&A in just a few minutes. So first up, let's hear from Mel Char at Mitacs. Mel, welcome to Open Hardware TV.
Thank you, Rick. Let me start by introducing Mitacs. We're a private, not-for-profit organization funded by the Government of Canada and all the provincial governments. We have the mandate to build bridges between industry and academia. And we have been doing so in STEM area, in social science, in health science, and social innovation. Recently, we've added business and law. In the last 20 years, Mitacs has completed over 19,000 projects. And I am glad to inform everyone as well that in 2020, we responded to the Canadian government call to action to support the special grants for the pandemic. And we worked with SMEs who were trying to pivot their business to adapt to COVID-19 pandemic. And during that year, we put together close to 15,000 projects, and that translated to about 5,000 years worth of research. Mitacs comes from the history of trying to put together these projects to create a couple of things. One is economic growth at the national level. We have mandate from the provincial and the federal governments, and we try to answer those mandates throughout the year. We usually look at economic development and economic growth in everything that we do. And the research that we sponsor or co-sponsor is actually tied directly to the industry. So from here, I want to try to explain to you why did we take part in the Open Hardware Consortium. Rick and I met about a year ago when he was first presenting this idea to some couple of hundred people at Invest Ottawa. And right away, I realized that this activity is so important to Canada that I elevated its status within Mitacs, and I right away took the initiatives to become part of the consortium to support these projects that come to fruition, because I think what we need to create that knowledge within the Canadian community. We need to build that talent, and we need to put together this base in order for us to compete at an international level. The Open Hardware is actually stationed in Canada, and it's headquartered in Ottawa. So I felt that it's an excellent setup for us to use that vehicle to create that relationship, not only nationally, but internationally. We are very eager to work with community that's across the globe in order for us to promote these technologies. So next generation network, we all know is they're going to be needing a lot of smartness into, I call them smartness, I can call them other things like everybody's given them keywords from 5G, IoT, wireless, cloud, you name it, AI. But at the end of the day, what is it? It's a piece of hardware that we put some software on top of it, and then we actually communicate back and forth with that piece of or that object, control it, get their status report, and activate it or deactivate it, and so on and so forth. Now, having a platform where innovators and the next generation developers are going to be picking from without having to worry about royalty fees, without having to worry about security of these platforms, without having to worry about the stability of those platforms is key, because that basically cuts into the time to market and the advancement of these enterprises that are taking the risk. And I believe open hardware is an excellent venue for us to build that knowledge in Canada and to support all the future evolution of these next generation networks. So what we did with open hardware is we put together the OpenHW Accelerate program, and it's based on Mitacs Accelerate. However, we tweaked it a little bit to answer to the needs of those industry partners based on Rick's background, the members that we have in the consortium, and the value of the experience that Mitacs brings to the table. So we have a standard OpenHW Accelerate grant, we have a fellowship, and then we have an industrial postdoc. We named them, again, for those who are familiar with Mitacs, we named them very close to the Mitacs program, so there isn't a confusion. But for more information on those, just reach out to me or to Rick, and then we will be more than happy to talk to you about it. I'm going to close by telling you how you can put together an OpenHW Accelerate project. There are three ways. There's a call for proposals that are going to be going out on a regular basis. I advise you to actually apply for those. If you're looking to start a project and there isn't a call, you can reach out to me or to Rick, or maybe even to CMC, my buddy Hugh Smith, who will be provided to you. We actually look after the University Outreach Task Group, and our job is to try to work hand in hand with Rick and his team on the marketing side to promote new projects with under the OpenHW Accelerate. And then the third, and if you're an academic and you're looking for a sponsor, I recommend that you reach out to us, definitely, myself and you, and we will work with Rick to identify members of the OpenHW consortium, and if not, we even reach outside the consortium to see if there are interested parties in this research specifically. We're more than happy to help you. Thank you, Rick. Back to you.
Great. Thank you, Mel. Now I want to turn it over to Gord Harling, CEO from CMC Microsystems, to give an overview of CMC and let us know why CMC is participating in this project. Gord, welcome to the episode.
Thanks, Rick. I'd like to talk about CMC for a little bit. CMC offers a variety of services to Canadian academics and industry, including CAD, tools in the cloud, and also cost-shared fabrication for things like microelectronics, MEMS, photonics, nanofabrication, artificial intelligence and machine learning, and as of last year, quantum computing as well. So we support both academics and industry. We operate one of the major science initiatives, one of only 16 in Canada, called Canada's National Design Network. And it has 67 universities and colleges in the network. So 10,000 academics use the tools every year, and about 1,000 companies design, build, and test prototypes. We have a worldwide supply chain, and we operate fabrication facilities all around the world, or I should say we access fabrication facilities all around the world. The Open Hardware Group and this CORE-V initiative is a great fit for our mission because we're trying to lower the barriers to technology adoption of SMEs in Canada specifically. So a common design platform with proven design flow and peripheral IP is very important. And getting the whole flow right through to test is a source of great pain for many researchers. So we try to alleviate that. We find it very important to have open source release of the code. When we fund a project, we ask that the project, 80% of the project be released as open source code for other people to build on. And we say to our partners that the 20% that's going to get you a Nobel Prize or is going to make you $1 billion, hold on to that, but do give us a portion of the code that we can release. And this silicon-proven RISC-V vector processor is going to be very important. The silicon-proven is a huge step, both in proving the technology and demonstrating the real fitness for use, but also in terms of training people. Seeing them take it right down to silicon, it makes them such a much better designer and tester. The extensions to the CORE-V family are something that we're funding now, and these are generally hardware offload engines that do various things like DNA analysis or image segmentation. Again, we fund those through academics, but often with an industry partner. And we have a proven track record in technology development. We have internal technical teams for microelectronics, for embedded systems, packaging and integration, and for AI and machine learning. We can do design reviews and manufacturability analysis. We can provide embedded software development, and we have manufacturing support. We build over 300 devices every year in the various technologies, and we carry many of those through to device packaging and testing. The core of our mission is really developing highly qualified personnel. And so this collaboration between ETH Zürich and Polytechnique Montreal is very important. It will grow our capacity domestically, but also bring in some of the best ideas from international partners. And so we see this as a win-win for Canada. Finally, there are huge growth opportunities in machine learning. Canada was an early supporter of AI, and they supported design groups and in various clusters around Canada. But since then, many countries have adopted AI as a key area of focus, specifically the US and China. And so the barriers to entry have risen as it's become more complex to access. So a common design platform is an efficient, cost-effective method for SMEs and new entrants to actually play in this market. And we think that the real strength for Canada is in edge applications, where we can provide niche, high-value sensor design and manufacturing of IoT devices that will go into agriculture, into Industry 4.0, into healthcare, and we'll be using the CORE-V VEC platform to lower the barrier so that they can actually build these devices and create innovative new IoT devices.
Great. Thank you, Gord. Next up, we have Frank and Mitacs from ETH Zürich to give us a history on the Pulp platform at ETH, as well as the specifics of the vector research that team has had underway for a few years now. Gentlemen, welcome to the episode.
Thanks, Rick. I'd like to talk today about Pulp platform, our project, our headline project that we started in 2013. So this is a collaboration between ETH Zürich and University of Bologna, and we started it when Luca Benini joined as faculty in 2013 at ETH Zürich. It's a fairly large group, 50-60 people spread over the two campuses. So we have our group here in Zurich, as well as another 20-30 people in University of Bologna. We work on different fields. There are people that specialize in hardware. We have people that specialize in software, applications, system development, you name it. What we are most known for is developing actual working integrated circuits. And just out of this project in the last 8 years, we were able to manufacture, test 40 ASICs, 40 integrated circuits in various technologies, the most modern ones being in 22 nanometers. We have a website where we have a chip gallery that you can access on the ASIC ETH.ch. And this has been a significant factor that we have both open source hardware, and those hardware resulted in actual working chips, has brought us closer in relation with the industry. And over time, we have realized that what we are doing is also relevant for the industry. This has led to the collaboration with the Open Hardware Group. We were approached by Rick and said, guys, I like what you're doing, but maybe your systems, the things that you have developed, are ready to graduate from a university to an industrial environment. We need to take them, nurture them, and give them a real home. And so far, a number of our cores and a number of our systems have already been migrated to the Open Hardware Group. We have a 32-bit processor that was very popular that is now under Open Hardware Group. Also, we have the processor that we called Ariane. Now it's called CVA6. It's part of the Open Hardware Group portfolio. If you want to know more information about it, we have a website, pulpplatform.org. We try to keep most of the information on this website. This website contains training videos, news, and most importantly, all papers that we have published about Pulp, our systems, energy efficiency, as well as all the presentations that we have made at various venues. We publish exclusively on GitHub, so you can go to our GitHub page and download the projects we are working on. And these projects are the ones that we also use in our design. So all of those chips that you have seen were manufactured using content that is also available to the whole world on the Pulp platform using a permissive licensing scheme. If you are interested, we have a very lively Twitter page. And in this Twitter page, we share news and stories, and it's a little bit lighthearted. You see our mascot, Bianca the bear, is greeting you all the time, and you can learn about what we are doing. So why are we here? We have an exciting new project, and this is the part that I like really a lot about open source, working in open source, because it allows us to collaborate with people all over the world. In this case, we are very lucky to be able to discuss with our partners from Canada. I will now hand over to Mateus, who is going to talk about RISC-V vector extensions and what we are going to do in this project.
Thank you, Frank, for your introduction. And I guess we cannot talk about this project without talking about RISC-V vector extensions, which is RISC-V take on Cray-like processing. Here, with the Pope group, we have ARA as our vector machine. ARA was initially my master thesis project all the way back in 2018, all the way back when the vector extension was based on the version 0.4. Both ARA and the vector extension have been developing concurrently, and we are happy to be able to release ARA openly, with the link which is showing the screen. However, our research with ARA is not done. We want to keep working on it, mainly by improving the energy efficiency of this design. First, by implementing autonomous memory subsystems on ARA, but also by adding ISA extensions for low precision computing. And of course, implement ARA in a modern technology. So that's it. Thanks for listening. Back to you, Rick.
Great. Thanks, guys. Next up is the team from Polytechnique Montreal, Yvon Savaria and Hossein Askari, to give us an overview of their research work and their objectives for this research project. Welcome to OpenHW TV, guys.
Thank you, Rick. So I'm here to talk about our participation at Polytechnique Montreal with this very interesting project aiming at developing a RISC-V extension to the ARA processor, and the part that will be done at Polytechnique. So let me talk a little bit about Polytechnique. Polytechnique is one of the largest engineering school in Canada, and it's located on the campus of Université de Montréal, which is the largest French-speaking university-level institution in Canada. So Polytechnique has 9,000 students. So you see on that slide, it exists since 1873. So it's almost as old as Canada. So if I can now talk about the project itself. So it's about RISC-V. It's about vector processing. And the objective is to do high-throughput multidimensional sensor data processing and machine learning at the edge. And that project is a research partnership between the OpenHW group, CMC, ETH Zürich, and the group that I'm leading at Polytechnique Montreal, the GRM. And today you'll hear from our group from Hossein Askari, a PhD student working with Professor David and myself. And so I'm Yvon, as you know already. The project is about extending ARA support for vector bit manipulation. It's also about adding support for vector mixed precision operands, and also to validate that this core is properly operating or is delivering as expected without bottlenecks. And we wish to improve the RISC-V software also ecosystem for that accelerator, because without a proper software support, that kind of accelerator is in fact not delivering to its full performance. So, and we want to do that in order to well support the vector instructions. And an important part of that project is we wish to be able to implement as part of the project a prototype, a microelectronic circuit prototype, an ASIC with Global Foundry 22. And that's really thanks to the partnership with CMC. Otherwise, we would not be able to do something like that. So microelectronics research group at Polytechnique, how did we arrive at that project? Well, I have been involved with developing accelerators for a long time, in fact, more than 30 years. So, and the microelectronics research group there is working on various forms of accelerator. And the idea is when a software runs too slowly on a general purpose processor, we start thinking of having some sort of an accelerator to improve the performance for the application. And the GRM then has been focused on designing effective hardware accelerator for a long time. And it's important to mention that effective accelerators are typically developed with some application in mind. There are no accelerator that will be a one-size-fits-all for all possible application. So it has features, qualities, and limitations. So that's one thing that I've learned to do for a long time, which is to explore relationships between applications, architectures, means of configuring that accelerator, and of programming it. Because if you cannot program it, you cannot use it. And we explored recently vector engine as a means to do better for 5G telecommunication. So this is where we gain some deep experience with using vector processors. And we also explored several architectures for machine learning and machine learning accelerator, the so-called ML accelerator. And we also recently explored how to use low resolution arithmetic in ML accelerators. Now it's time for me to hand it over to Hossein to give you more detail about what we're going to be doing.
Thank you, Ivan. So we found RISC-V as an excellent choice for exploring different architectures and research ideas. We've been, in the past couple of years, we've been developing RISC-V based processors, and we proposed the asynchronous designs, which was adopted by one of the Montreal-based company. We've also explored the idea of extending RISC-V for machine learning applications with a collaboration with IBM and Mila. In the last 2 years, we've developed an accelerator with a RISC-V barrel processor as a controller to control ML accelerators in low precision. So our part for this project would be extending bit manipulation ISA and CORE-V vector processor. And the idea here is to add the support for using low precision operations such as pop count on GORC. And this is based on our extensive research on binary neural networks. We will try to add these instructions to RISC-V ISA in vector extension. Thank you very much, and back to you, Rick.
All right. Thank you very much, gentlemen. All right, welcome back. We're just about to get started now with the live Q&A. We have a bunch of very interesting questions that have come in. If you have topics you'd like to see covered, please don't hesitate to type them into the Q&A window. We had a message from a few viewers that for whatever reason the Q&A window on their Zoom platform wasn't working properly. So feel free to put your question in the chat box and just address it to the panelists if need be. But the rest of the guys are all back on. You should see everybody here from a panel standpoint. And the way that we run these is I'll curate, if you will, the questions coming in on the chat box in the Q&A window and throw it out to the panelists and put them on the spot, so to speak. So feel free to have some fun and poke the bear, so to from time to time, and see if we can get a lively discussion going. Ideally, we're all in the same room together with a beer in our hand doing this. So let's pretend that that's the case and have a good discussion. Oh, I think Frank's going off to get a beer. It's almost a beer in Gord's hand, so we're all good. There we go. He's got a Nurkel. Open it up, buddy. All right. So a couple of questions around the spec, and if you've been following along with the RISC-V vector extension (RVV) and the evolution, as Mitacs mentioned in his talk, the team at ETH started back in 2018. More probably earlier than that, but 2018, the first .4 version of the vector extension spec was out there, and people started developing against it, and that it's since migrated quite a bit. So we had a question around specification compliance and what are the plans or objectives with this project relative to the RISC-V vector extension specification, the standard being released, soon to be 1.0 released, or a 1.0 candidate release from the RISC-V International Foundation. So, maybe Hossein and Frank, I'll let you guys each take a crack at that. Frank, do you want to go first?
Yeah, first of all, for the compliance, it was very difficult, as you mentioned. It took quite some time to develop. It's still not finished. So 1.0 is about to be released. And we were able to release, as ETH Zürich, the 0.9 version, compliant version of the ARA. And as part of this project, we want to do more. But this is not an industrial project per se. These are two research institutions trying to figure out what else can we do. Will this work? Will this not work? And we are inspired by the bit manipulation extensions that are being proposed. We are also involved in those, and we want to try things out. So this is why it's nice. This is why it's fun, and it's a great opportunity being provided by Mitacs, OpenHW Group, and CMC that allows us to explore things. So I think this is the thing what we are mostly excited about.
Thanks, Frank. Hossein, do you want to comment on your experience with the spec and tracking it?
Yes. So in Polytechnique, we're mostly interested in low precision machine learning applications, and ARA is like a great platform for vector processing and obviously for machine learning. However, the bit manipulation has not been extended to vector extension as far as I know. So one of the approaches that we want to study in this project is try to figure out what are the chances here and what are the opportunities to add this to a vector processor like ARA. And so mostly like bit manipulation was just an idea to start with, and we want to extend on top of that.
Right, and I'm going to add to that a little bit from the standpoint that what the focus in the OpenHW group is covers the waterfront from research-oriented engagements such as this one, right through to hardened, production-ready RTL that is well verified and used in high-volume production SoCs. And we really want to have the big R, little d aspects, and this if you think about a company with an R&D organization. This project is in the big R, little d end of the spectrum, whereas the work that we did, say, over the course of last summer, as we achieved the RTL freeze milestone on the 32-bit core that originated at ETH Zürich, the RISC-V core that is part of the CORE-V VEC E04 family. And we reached an RTL freeze milestone in December after having gone through a very industrial-grade, high-quality verification project. So the philosophy within the OpenHW group is to embrace the research roots, if you will, of our organization, stemming from the early relationship with Luca and Frank and their teams at ETH, have a big R aspect to the projects that we curate, and have a path to full commercialization of that open source IP and deployment in high volume production SoCs. And this project is at the front end of that work. So a couple of other questions came in related to that. And in particular, the extensions that we want to define with respect to bit manipulation, low precision arithmetic support, and so on. How are we going to do that? Are we going to propose a new standard, or what's the approach there? And this probably goes back to Frank and Hossein, but maybe we'll flip the order and I'll put you on the spot first, Hossein.
Yeah, so mostly I don't, at least for the period of this project, there may be a new extension, but I'm mostly interested to see low precision application with the software support on ARA. So as we mentioned in the presentation, some operations like GORC or pop count are very suitable for low precision application. And we're mostly interested to see that in a like actual ASIC. So that would be, I think, one of the things that we're going to explore at the beginning.
As far as standards go, or standardization goes, yes, obviously, we believe we have some good ideas. We believe they will work well. And it's now part of this project to show what they can do. And we will see the results. And hopefully the RISC-V community will take notice and it will have its due process. And we hope certainly that some of the things that we are proposing will make it into one form or the other into the standards. But I don't think the success and failure of this type of project is measured by how much of it gets ratified in the RISC-V standards.
Yeah, no, I'd agree with that. The other aspect of what we're trying to do in the Open Hardware Group, and this is specifically related to extensions and whether or not they're standard and so on, is within one of the strong aspects of the RISC-V ISA is that it is includes a user-defined instruction space, and that's a reserved space where you can capitalize on the fact that the ISA the specifications cover a generic ISA with all of the instructions that you'd expect, and then add your own secret sauce in a user-defined accelerator in this custom space. So we're working on a series of specifications called the CORE-V extensions interface that tell you how to add new instructions in at the RTL level, at the tool chain level, what you have to do to compilers and your tool chain to take advantage of that, how you need to modify your verification test bench to make sure you didn't break the original core to begin with while adding new stuff, and make sure you cover the new stuff that you've added, and then any OS hooks or platforms depending on what you're running in terms of operating system. And while it's good that the ISA has a user-defined space, making it easier and more accessible to create those user-defined custom extensions is a good thing. And whether it makes it into a full standard, like Frank said, that is adopted as a new standard extension, or whether it's a de facto industry adoption because we have a user group that has all agreed to use these custom defined extensions in a certain fashion. That's also, an applicable way of taking advantage of the flexibility of the RISC-V architecture. And Gord, I'm going to throw it over to you because one of the things that we've been talking about here has to do with a common platform that then others can build on and reuse that platform in research and so on. And it speaks directly to adding the secret sauce in the user-defined instruction space. Can you speak to the requirements of your users and what you're trying to serve in that area?
Sure. I'm actually going to skip ahead a bit because there's a question about packaging and making that easy for folks. So these designs will be implemented in 22 nanometer RFSOI at Global Foundries. And when we've got a chip out, we will put it onto a daughter board, and the daughter board will plug into a low-cost FPGA board. So you'll be able to concentrate on the RISC-V, to concentrate on your offload hardware, and then access peripherals for Wi-Fi or Bluetooth or SCSI disks or whatever via a motherboard. And so we're trying to make it really simple and pluggable, and we'll have a standard interface for that for those daughter boards, and we'll generate those boards for each chip that comes out if the customer wants it, obviously. And if you're going to do a full-up commercial design, then you'll go out and buy the IP for the peripherals, and you'll implement your RISC-V and whatever other elements you need on chip.
Thanks for answering that question. I was going to get there. Flip back to the other question, if you don't mind, while we're staying on common platform and customization.
So as time goes on, we will be as a stepping stone, as something to build on. when we fund a project to develop specific offload hardware, we will make it available on our GitHub so anyone can download it and use it. And there'll be both software and hardware there. And we'll have the Gerber files for the PC board if you want to do your own and so on, if you want to modify it. So you'll be able to look in there. And as I said in my little video clip there, we want the people we fund to give us some portion of the code, something that's useful for other folks to build on, standing on the shoulders of giants, right? And improve and enhance and do their own thing, but lower the barrier to diving in and starting from scratch.
Okay, great. Thanks, Gordon. Going to change gears a little bit around sort of the business aspects or funding aspects of these projects and the group overall. So we had a general question around the tools and people funding and where it comes from, and specifically, Mitacs, how's Mitacs funded, and CMC, are they funded? And is Open Hardware Group a research organization, or what are we? So why don't we start with you, Mel? How is Mitacs funded, and what's your mandate?
Thank you, Rick. Great presentation by everyone. This is the first time I've seen it, and great answers. As I mentioned in the video, we are funded by the federal and provincial governments of Canada. And I want to step back and then talk a little bit about the what we have at the moment here with Open Hardware is, let's not look at Open Hardware as a company. It's actually, it's in the inception of where we're building a platform where people can stand on or can use to go forward. So from a Mitacs perspective, we're trying to help that R and a little bit of D so that we can get things moving slowly into the development and into the production. So with the combination of what's happening with all the people on the table here, we're hoping that this wheel starts to turn, and eventually it will be rolling and it will become an ecosystem that's growing and providing access to all of the contributors or innovators. So from Mitacs perspective, we're looking to actually partner with anybody who's going to be around this ecosystem. But if I want to step a little bit on the side, Mitacs can help all the participants, not only on projects or on funding from Mitacs. We can work with them to see how we can solidify their ability to access other funding, because Mitacs has a lot of collaboration with NSERC, with NRC, with all of the other granting organizations within Canada. So I recommend exploring on a project by project basis and getting us early in the discussion to see how we could, get you guys benefiting from all of that connections that we have.
Thank you, Mel. What's interesting actually for us is we're going to have a hard time as an ecosystem in the OpenHW Accelerate program spending the amount of money that we have available to us. Bringing the industrial research sponsors to the table to take advantage of these funds. Gord, I'll throw it to you in terms of, I know you covered it a little bit, but just CMC sort of funding and mandate, and then I want to talk about tools, commercialization of tools and access, because so far, primarily the Mitacs money gets spent on funding researchers in academic institutions, and that's what that's for. So Gord, give us an overview of that from CSC's perspective.
Oh, sure. So we support research and in 3 different ways. We have CAD access, computer-aided design tools. We have a cloud. We operate all across Canada. We provide those tools to 10,000 researchers in academia, but we have a new program called VIE, V-I-E, and this is for startups. And so we are in a larger and larger way providing CAD tools at almost academic prices to small startups who can't otherwise afford them. So the vendors see their interest in this because they're giving you a taste, they're getting you to your minimum viable product, and when you get funded, they'll hit you with a bill for the commercial tool. If you're fabbing, we offer these shared wafer services. So our interest is really in driving more people to use our CAD tool offering, to use our fabrication offering, and to build these chips. And we can help you not only with cost shared prototyping, but also mid to medium, low to medium volumes. So we actually do dedicated wafer runs for some of our customers. So we're really there to try and turn this academic research and these RISC-V variants into commercial products and get them launched in Canada. So very exciting times. And the more we can demonstrate the capability of the RISC-V processor, whether it be 32 or 64-bit or an edge computation or in different applications, the more customers we have who will come to us and look to do their own custom development. So we're sort of generating use cases and demonstrating the capabilities, and there'll be technical papers written, and hopefully that will drive commercial companies to come to us and say, we're really interested in a benchtop DNA analyzer. You've got this chip that does X, Y, Z. Could we do one that does this much more? And we'll find them a partner, we'll get the design done, and we'll help them to broker the fab and get it done quickly and cheaply. So that's really our drive, is to push more RISC-V variants into more commercial, into more academic kind of hands, and demonstrate the capabilities to commercial customers.
Right. And so in the open hardware group, the way that we fit into that whole structure, both Mitacs and CMC, for the most part, are government-funded organizations. CMC also has a non-government revenue stream as part of their mandate. By comparison, Open Hardware Group, we're essentially a private corporation. We're a non-profit private corporation, and we're funded by the members in the ecosystem. So it's a privately funded, if you will, because it's membership driven. So we're not a research institution. We're not a government institution. We're an open source ecosystem that is privately funded by the members that participate and have a like-minded goal and objective of curating open source artifacts for use in high volume production SoCs. And as such, all of the tools that we use and the way that we drive the projects through to the RTL freeze milestone that I mentioned earlier for the 32-bit core, the CVE4 family, is all commercial tools, right? So we support, we're a system Verilog house. The way to think about Open Hardware Group is we're a private IP company. We sell, quote unquote, IP for free. Right? It's open source, permissive license. You don't have to be a member. When it's up on the repo, feel free. Everybody can use it. So everything that you'd expect to see in a commercial IP company is what we are implementing, projects to implement with over 63 members and partners, as I outlined earlier. We standardized around system Verilog implementations. So all of the RTL that we work with is system Verilog based. We have commercial quality verification test benches around the RISC-V cores called the CORE-V verification test bench. It runs on all 5 of the commercial system Verilog simulators out there, from Cadence, Mentor, Synopsys, as well as Aldec and Metrics. So there are make files to let you build and target all 5 of those system Verilog commercial simulators. It's a UVM-based verification methodology. Leverages commercial reference model from Paris. It's a very, very strong, high quality commercial verification infrastructure. And the reason that we do that is so that there's high degree of confidence by large SoC companies, systems companies who want to build high volume production SoCs out of this IP. We need to make sure our IP flow fits into their IP flow. And 95% of today's semiconductor volume is built and verified in a system Verilog UVM-based flow. And that's principally why we're structured that way. So the only real difference that you should think about of the open hardware ecosystem from a commercial IP company is that instead of being a private company with proprietary IP, with IP that is licensed or sold with a royalty, it's an open source company with contributors from all over the world, a distributed development team, if you will, curating and advancing the quality of open source implementations and all of the support infrastructure around that, including software tools and the operating system ports and FPGA bring-up boards, as well as ASIC volumes and production. So speaking on the ASIC side, we're going to maybe change gears a little bit to the volumes associated with what's been built before, how much of this stuff's been validated. So there was a few questions around all the lovely picture of 40 some odd ASICs from ETH. What kind of volumes are we talking about? How do we, how is CMC producing volumes? What does, and I'll talk about the Open Hardware Group and our foundry relationships as well. So for ERA specifically, I know Frank just wheeled to the back of his room there. I'm sure he can hear me. He's going to have a show and tell object in a moment. Can you talk about the kinds of volumes that you guys have built? I know it's all been MPW, but people want to know what's gone to production and in what kind of volume. So Frank, can you talk about that a little bit?
Yeah, so we are a research group. So we mainly manufacture things in MPW. So what you get back is a small thing like that. So when it's packaged, you maybe have 10, 20, 50, at most 200 chips that come back. The usual amount is around 50. This is enough for us to evaluate our systems, build some demonstrators, and show how we are doing. For larger volumes, we leave that to our collaborations, companies, members of the Open Hardware Group that have business interests that reach beyond what we can show for research purposes.
Right. And Gord, some of the early ramp stuff that you talked about, what are some of the volumes that you would typically be engaged with in terms of the different clients that you serve, both from academia and some of the younger SMEs?
Yeah, so historically, we've done these multi-project wafers, and with Global Foundries, we have a great relationship, and so we can sell you area by the millimeter squared. So it's you don't have to pay minimum fees or any of that stuff. We do that, we buy it, and then we share it among a whole lot of users. So typically you get anywhere from 40 to 100 pieces on your first run. So that's enough for you to make sure that it's working, debug it, and so on, and you're not paying for tons of inventory. But they also allow us to do dedicated runs. So we can run 12 or 24 wafers for you if you want. And Global would not take you on as a customer if you're that small a volume, but they allow us to do that. So we broker all of that stuff for them. And when you're up to 1,000 wafers a year, you go direct, then we lose you. That's fine. We've done our job.
Right.
Yeah.
Right. And so carrying on.
And if you want package and testing services, then we work through partners to do that as well.
Right. So carrying that flow through from an open hardware perspective, so Global Foundries is a member of the Open Hardware Group ecosystem and a strong partner, and we're leveraging similar relationship that Gord just explained. Our programs with Global are such that we'll produce up to 10,000 pieces of a design. So we have a CORE-V MCU project underway right now that integrates the 32-bit core that I talked about earlier, which will be put on eval boards and produced in up to 10,000 pieces. It's not a production device. You can't buy it from Open Hardware or any chip company. Any chip company is more than welcome to take the design and make it their own. They're certainly permitted to do that, and it's a very exciting project, this CORE-V MCU project. We'll do something similar with the Vector project, CORE-V VEC. That sits alongside the CVA6, the Ariane 64-bit processor. Probably not right out of the gate. I mean, there'll be some smaller volumes that we'll play with first, and then we'll eventually have some kind of a development platform that we will produce, like I said, up to 10,000 pieces and get that into developers' hands and make it more accessible. And part of the aspect here is, sure, I mentioned the big R to little d, and as we start to transition to an uppercase D, if you will, in that flow, having the complete flow right to gates. I think Gord talked about this earlier, is an important aspect of the enablement not just from a fit for purpose of the design, but also from an enablement of the software and firmware ecosystem that gets developed around it. So we have a few minutes left, and I want to transition to the software side and the toolchain side, specifically on the vector processor research project. So this is going to go back to Hossein first, and then Frank, around the tool chains that we're going to employ, and actually we do want to save a little bit of room at the end for how other companies can participate in this project now that it's defined and started, because this is not a closed project. Well, we welcome other industry participants. So Hossein, start us off on your view of the kind of tool chain work that you expect to see and happen over the course of this research work.
So hopefully, thankfully, there is a healthy, ecosystem around RISC-V. So any extension that we're going to build will definitely be on top of that. So RISC-V, Spike Simulator. So these are very good that we can use in our project. But from machine learning down to silicon, there is a big gap right now. So we have to customize some of these tools from model in TensorFlow or PyTorch to bring it down to what we have in R as a vector processor. So there are going to be a lot of tools that we're going to use, but we definitely need the help on extending some of these tools for bit manipulation or do binary operations. So some of the work that we're going to do will be customized for this particular chip that we're going to build, but I think there will be generalized enough to be extended for other projects with similar architecture.
Frank, anything to add? Go ahead.
The great thing about RISC-V is that, you can leverage all existing RISC-V works also in the projects as long as you remain compatible. So for the parts where there was also a part that was asking, how do you comply with RISC-V specification? We want to comply as much as possible because we want to use as many tools, standard tools, LLVM, GCC, and all those new vectorizing additions to those things as much as possible. Once you start making add-ons, you have to find ways around it. In the beginning, obviously, this will be, let's say, handcrafted inline code so that you can do your experiment on microkernels. Obviously, going forward, you want to leverage these tools and make your own additions or have your suggestions there. But the idea is clearly leveraging the available open source tool chains.
Right. Okay, so I'm going to kind of wrap it up with trying to summarize a question about how can people participate, and in particular use some examples around the tool chain and the and verification infrastructure. We had a lot of questions related to just tools and quality and all that good stuff. So this is a project that's defined from a research infrastructure standpoint, and that's great. There's lots of commercial tools and open source tools on the software toolchain side, SYCL and different ML focused tools that are appropriate here. Commercial companies who want to participate and support this research group with availability of those tools and binaries and so on. Perfect. That's an excellent way to participate. The same with on the verification side, companies with verification IP or reference models and so on that want to help stand up a test bench so that the researchers aren't spending time putting verification plumbing in place. They're just leveraging the fact that there's some standard flows out there. We're going to have part of our verification task group will be a test bench to support this project. So the open hardware ecosystem will be participating in that fashion. And the other thing about the OpenHW Accelerate in general, this is the first research project under the OpenHW Accelerate program. And we are looking for more. We'll have calls for proposals, we'll have research requests, but we're looking for more projects that fall into those tracks that I mentioned earlier in the recorded part. So if you're in industry and you want to co-sponsor, basically double your money, so your research dollars get multiplied by 2 by the Canadian federal government and then deployed into the research infrastructure that we have here. we want to hear from you about those projects. And this is a very exciting first initial one to show, if you will, as an example of how to take advantage of the OpenHW Accelerate funding program. The last thing I want to mention before we wrap up, it is the top of the hour, is coming up on the 1st of April. Yes, it's on the 1st of April. As part of RISC-V week in Europe, the third RISC-V week, I think, that the European community has run. On the 30th and 31st of March are 2 days of RISC-V week. And then on Thursday, the 1st of April, is an event called Open Hardware Day. And we will have a full day worth of tutorials and overviews of the various projects underway within Open Hardware Group, as well as the specific needs and support for the European community in terms of curating more projects specific to Open Hardware Europe. So if you're interested in that event, just go to the openhardwaregroup.org website to find out information in the event section, and you can Google RISC-V week to find it, or Open Hardware Day to find it, and we hope to see you there. So thank you to our panelists and all of our attendees. I hope this was informative. If you need more information about the Open Hardware Group, please reach out. I would be happy to talk with you. Thanks very much, and wherever your day is, I hope it's a good one. Bye for now.